I really am thinking of a series of this one.
Yeah.
And so there, the A sub n is different than A sub n in the alternating series test.
Yeah, so then why isn't the alternating series test the only test that we can use? Because unless it goes to 0, it's still going to be alternating between some values.
It's just because when it comes to the radiation root test, these series we're testing do not have to be alternating, but they also apply to alternating series.
Right.
So if you got an alternating series, you've got a lot of options in terms of what test to apply. I just maintain that to use a ratio of the root test, the series itself doesn't have to be alternating. There's a difference. I don't know if I'm answering your question.
I was just going to ask is, before you move on, if it's possible, can you take a couple minutes and maybe explain that again, how you jump from that cute little C,
Yes.
make it into the beautiful C to the beautiful F?
Yes.
I understand the substitution after that, but I don't understand how you got.
The C, how the Cn became the Fn.
I know you did that thing.
Yeah, and how that
This one
correlates to
seems
the
junky
definition.
for me. I mean, maybe I'm putting.
But this is the answer to everything. Because I think it's Qn. And what you've got to do is Qn on how I played a silly game. I said if I express my function f, if it is expressible in such a fashion, that is to say as a power series centered about x equals a, notice something really cool when I differentiate repeatedly. All my terms on the right-hand side involve a factor of x minus a, well, except for the first term. They're just constants. That being as is, what's really slick about this, with the original function, if I evaluate x at a, everything drops out except for that first term. There it is. I circled it. Now with my first derivative function, I know things are changing on the right-hand side, but if I put a in for x, everything drops out over there except for the first term. There it is. Same thing with the second derivative. Same thing with the third derivative. What I want you to notice, however, that there's a pattern here. Here's the third derivative, but it's just 3 factorial times c sub 3. And so I think with the nth derivative, I'll get an n factorial times c sub n. Well, let me walk backwards. Let's try our math skills. If I isolate Cn in this equation, wouldn't I just divide both sides by n factorial? But that means that nth coefficient is just this.
So that's the formula is all the time trying to get
Well, if your function has a power series representation about x equals a, yes. Correct. What's that penny to throw? Okay, well, because I think I slip in another word. You know, sometimes a function's analytic. I think these books aren't. If a function has a power series, sometimes I say it's analytic about x equals a. And check out this function right here. I do not think I could find a power series representation for that function about x equals 1. In other words, if you look at the graph, I can't find a tangent length of the graph of f at x equals 1 to the vertical asymptote there. There's an example where my function f is not analytic at x equals 1. I have found a power series representation for it at x equals 1. And if you can't see why, go back over here. I think in each and every one of those derivatives, I'm still meant to find at x equals 1. So I'm not going to be able to come up with a constant c sub n. I'm out of luck completely. Now, Deborah, I have to confess, in this example over here, I do think I can find a power series representation about x equals something else besides 1. Like 2, 3, or 4, 5. Shoot. You know what? That's too good. Can I just steal it? Let's find a power series representation for this f. About x equals something like, how about a 3? David, thank you so much. No problem. To do it, I guess I'll come over here. And my function f has an output that is 1 over x minus 1. I think its first derivative is this. I think its second derivative is this. I think its third derivative is this. Can you guys extend this a little bit? What do you think you could say about the nth derivative? Oh, gosh, kind of going back to sequences, isn't it? I'm trying to find a pattern here.
A factorial
Negative
or negative 1
n factorial, you said, Sean, -1 to something, what was the something gonna be?
And
Yeah, I think it's a clean n, isn't it? Because the first derivative is odd. So when I plug 1 in here, I get a -1. And I think I'm dividing by x minus 1 to the m.
And 1 plus 1.
I think it's the n plus 1. One more power than the order derivative.
okay.
That being the case, a power series. I can spell power. I really can. Representation. For f centered about x equals, you guys, I'm making this number up out of thin air, about x equals 3, is the following.
So
It simply says that the output of my function can be expressed in sum as n range from 0 on up of my c sub n times x minus a to the n. Or shall I say, as n range from 0 on up, gosh, what do my c sub n's look like? I guess they look like the nth order derivative. That's right here. Divided by n factorial. All times x minus a to the n. Now, I admit, you guys, this example, I get a little lucky. I didn't realize this. I made this example up out of thin air when I put it over there in red. But it turns out to be the case that I do get some nice simplification, don't I? The n factorials cancel. Oh, did I mess up with this? Sorry, you guys, I did mess up. Isn't the exponent n? I forgot to put it in. I guess I got the sum as n places came of a -1 to the nth all over. You guys, I messed up somewhere else too, didn't I? What goes in here?
3.
Yeah, my a value. So I think downstairs I just got to 2 to the n plus first power times my x minus 3 to the n. Do you guys mind if I expand it out a little bit? Let's just play with this, see what it looks like. I think when n is equal to 0, I get 1/2. But I think when n is equal to 1, I get a -1/4 times x minus 3. I think when n is equal to 2, I get an additional third term, which is nothing more than, did I say n equals 3? I meant n equals 2. Doesn't that give me a +1 over 2 cubed times x minus 3 to the second power? Well, here too, I'm not trying to bore you guys, but I want you to see the significance in this. And see, the significance means I get to go to a funky looking picture. And in my funky looking picture, I'm going to type in into my equation editor my original function, which is 1 divided by the quantity x minus 1. Excuse me. It's just that. For what comes next, I don't know what's next. You guys help me with this. Is it 1/2? I don't know the rest of it. Minus.
Oh, 1/4 times quantity x minus 3 plus 1/8 quantity x minus 3 squared.
And I suppose I'd better mess around with this real quick. Is that going to be a -1 maybe? Let's change this like a +4. And I don't know what my scale is going to be. And let's see what it looks like. Well, there's my hyperbola, the function about which I'm trying to find a power series representation. And there's my power series representation, at least the first few terms, centered about x equals 3. Okay, so I messed up pretty bad with my x scale, didn't I? I forgot I'm centering about x equals 3. Let me move out just a little bit more. How about something like 7? Now let's see what it looks like. The original hyperbola. And the first few terms of my power series. Imagine that hyperbola pretty darn well about x equals 3, isn't it? I just think I can do better for greater values of x. You guys agree?
Yes.
I said for greater values of x. I mean, I can do better for a greater number of terms. My apologies. In the power series. By the way, in this example, do you think I'll always get an excellent approximation of my curve at any value of x? Just by adding more and more terms?
It depends what you're centered about, right?
I mean centered about x equals 3. Do you think the more and more terms, the better and better the approximation is for all values of x? For all of them?
If you go to infinity.
Problem.
So you're saying that a function that can be expressed as some constants times x minus a to the n, then you can go through all this nth derivatives and stuff like that. But since that's already in the form that you're trying to express it in, can't you just say that it's a power series of itself? Like,
See, I don't think it can for this reason. When you rewrite that over there as x minus 1 to some power, I think it's to the negative 1 power. And since n is ranging over non-negative integers, I'll never get the negative power. But you're right. If that were like x minus 1 to the third, no, it's kind of silly, isn't it? I've already got it in the sense of a polynomial function by like off. But I think you guys were a little off on this. See, I think no matter how many terms I can grab over there, it's never going to do a good job approximating my function's output, my function's y value, at x equals 1 where the vertical asymptote is. Maybe that means today or tomorrow, I need to start talking about restriction of the interval over which I converge. We call those intervals of convergence.
Radius.
Or radius convergence is how far out it goes.
So,
On a test situation, would we be given, estimate the power series to the closest 5 terms, or, I mean, how far do you?
I can ask a lot of questions. Here's one of them. For this function there in red, let's find a power series that's centered about x equals 3. Give me the first 5 terms.
Okay.
Or give me the Taylor polynomial to the 5th power. Now here's another question I could ask, but I'm not going to ask today. How many terms do you have to go out to get desired accuracy? Maybe 1/1000th over some interval. And I'll discuss it in class. I'm definitely not going to get that today. Okay.
so just a quick question. When you're finding the nth derivative, how many times should you differentiate before?
I don't know
you
the answer. It depends on
figure
what you
that out?
want. For example, I did a lot here. It's one of my first examples, so I did not carefully tell you what I really wanted to do. But you know, at this point right here, I think I did a pretty nifty job in finding a power series for my function f, and you can identify any term you normally please. But what if I asked you this question? Given that red function, give me the first 3 terms generated by the power series. I think all you really have to do is compute these few derivatives. Don't look at a pattern. I just want the first few terms. That would suffice, depends on what I'm asking for. But if I do ask for a power series, then I want all the terms, and there they all are. In nice, neat closed notation. That's slick.
So basically finding a pattern, just like we did in sequences.
Yeah, you're gonna have to find a pattern if you want some kind of formula representing all terms of the infinite series that represents your function. I agree.
This is where it all falls apart.
Yeah, just the thing that was tripping me up was, I see the n factorial in there, obviously, but, I don't know if that breaks a few terms down. I mean, that's just what.
And you know what, Bradley, you've got a good point.
Yeah.
Maybe for you, you might have to look at a few more terms. I don't for this
Okay.
reason. Watch. I mean, the next time around I differentiate, I'm gonna bring the 4 down with the power rule. Then
Okay.
5 down, then 6 down. I mean, to me, clearly, I got a factorial there.
Okay,
But like you just said, maybe you have to generate a few more terms to be able to see that.
okay.
You guys so far so good? Yeah, definitely.
Okay, so just step by step. So the one after you say about x equals 3, you picked the x equals 3, right?
I did, yes.
Okay.
I asked you to find a power series representation centered about x equals 3.
So when you
That's
ask
what
you
I
to do that,
asked.
you do the little derivatives
Yes.
and get the f little pretty picture over there.
Yeah, the pretty picture, yes.
And then you put f of x equals to cx over there.
Well, now, Deborah, I did put in too many steps, probably. You don't have to write this. I'm just being instructed in front of the entire class. You could have just immediately went to here.
Not probably do the same thing. The moment the n factorial and 3 minus
Yes.
1, that's just c. The x minus 3 is that x minus a.
Can I exchange another step you can put in between?
Yes, please.
N equals 0, infinity. The c sub n really is the nth order derivative, eval at x equals 3 all over n factorial times x minus 3 to the n. Now circle the n factorial, that's where this is. Box the nth order derivative value 3, that's where this came from the work over there. And I'm sitting there telling you I'm showing my steps. I should have showed that extra step there as well. Oh, you guys guys, how about another really fun one? What's the derivative?
E to the x,
What's the second derivative?
e to the
What's
x,
the nth derivative?
e to the x.
So I think to find a power series representation is going to be really easy. I think e to the x is simply going to be the sum, as n ranges from 0 on up, of c sub n times, can I do it about x equals 0? Times x minus a, which is just x, to the nth power. Or shall I say the sum of c sub n, which is something over n factorial, to something is the nth order derivative, divided 0. Oh, by the way, since the nth order derivative is just e to the x, that divided 0 is just going to give me 1. I think 1 over n factorial times x to the n is the power representation, power series representation for my natural exponential function. If I were to expand out, it looks like a 1, plus 1 over 2 factorial times x, I misspoke. I meant plus x. Plus 1 over 2 factorial x squared, plus 1 over 3 factorial x cubed, plus 1 over 4 factorial x to the 4th. Now the first term clearly is the constant function that passes through y equals e to the x at x equals 0. That's just positive 1. The first two terms constitutes the tangent line to the graph of y equals e to the x about x equals 0. I think the first three terms is the one best fitting quadratic function about x equals 0, etc., etc., etc. Actually, jeepers. Guys, I've got so many of these. The graveyard of pens.
Let's just toss them.
What's that?
Somebody gonna save them, or?
No idea what's going on. Well, let's check out what we have so far. Don't look, you guys, yet, because I might be sick. So let's check out what I've derived so far. I've derived for you the power series representation for natural exponential functions centered about x equals 0. That's exactly what I have over there. I've also generated the cosine function. Can I skip this one, you guys? Only because it's so similar, and the author does it for you anyways. The technique's identical. There are quite a few in here with which I expect you guys to know. Before you came in today, did you know this one? I said, before you came in today, did you know this one? I can ask that again.
Yes.
Yeah, you did. Come on, now.
It's a geometric series.
Yeah, I think it's just a regurgitation of the geometric series. After all, when it comes to the sum of a times r to the n as n ranges from 0 on up, you guys humor me. Don't you simply get this? Hello, anybody?
Yes.
Good, one person agrees. And by the way, I do think that if I asked you to consider the sum n ranges from 0 on up of x to the n, it's the same thing. Just a is 1, and r is x. And I think it's going to converge as long as the absolute value of x is strictly less than 1. Oh, by the way, when it comes to this 1 plus x squared plus x cubed, as long as it is the case that the absolute value of x is strictly less than 1, I think the sum is my a over 1 minus r. So I think that function right there has an output that can be expressed as such. So in other words, for f of x being equal to 1 over 1 minus x, there is a power series representation. And I think it's just a regurgitation of nothing more than the means by which you and I compute infinite geometric series. So how can I come up with this one? Shoot, it's a piece of cake. I'm simply going to come in, you guys, and I'm going to replace x with, negative x. Next, I think when it comes to something like, I hit the wrong button, sorry. I think when it comes to something like 1 over 1 plus x squared, this can be interpreted as, actually, can be interpreted as nothing more than this, with x being replaced with negative x squared. Or you, down here, replace this x with x squared. I think that generates a 1 minus x squared plus x to the 4th minus x to the 6th. Are you guys with me? Let's have some fun. On the right-hand side of the equation, I think life's easy.
Why?
Because something nice happens on the left-hand side. Besides, because I can. Then I get this.
Yes.
Over here, don't I get this? Nah, I made a mistake, sorry. I meant to say, I get this. Did you guys agree?
Yeah.
Are we nice and awake? No, you shouldn't agree. I did something wrong. What is it?
Didn't add a constant?
Thank you. But to find the value of that constant, can we just take a break? Can I plug 0 for x? On the right-hand side, what do I get when I plug 0 for x?
0.
Zero.
C. C.
Or
C.
C.
And on the left-hand side, what's the tangent of 0?
5 halves.
I can't hear you.
0.
Yes, it's 0. In spite of they see ends up being 0. So in the end, I guess it didn't make a mistake, but I gotta consider what the constant is. You wanna see something really fun?
Yeah.
Want to see something even funner? Isn't that slick?
No.
Yes, it is. What's the inverse tangent of 1?
Pi.
Well, pi
Pi,
quarters.
yeah.
Check that out. You and I now have a means by which we can approximate pi to any darn desire of accuracy we want. Because an alternating series is as close to what you want up to the first unused term in the absolute values. Isn't that really cool? Come on, you guys.
Yeah.
Okay, good. Let's open this up. David, you don't agree. What do you guys think you could possibly say about this? Just panic. Say something.
E.
Well, that is something. Oh, you guys really? Anybody?
Hold on, let me do it all out in my head.
Yes, I wish you do it in your head. You just look to the left-hand board.
1 over 1 minus x.
Are we just going to anti-differentiate both sides? And if I were to anti-differentiate both sides, on the right-hand side, we're going to get this. Oh no, you guys, we don't. I made a mistake. I really did. Because I think when I anti-differentiate the left-hand side, I don't really get the natural log of this stuff, because when I make a u sub, I get a negative on the outside. So I think multiplying both sides by -1, I get this. Oh, by the way, the constant's in the way. So if I were to plug 0 for x everywhere you see everywhere, don't you think that negative c is equal to just 0? It's gone. What if I asked you to give me a power series representation for this? Any ideas?
Cry.
Cry. Don't cry. Anybody?
Partial fraction.
You know, when it comes to a power series, though, I don't know if I really care about breaking this up into sum of 2 different fractions. I was hoping you'd say, just take a peek over here, and instead of integrating, we'll differentiate. And if I differentiate both sides of that equation, I think on the left-hand side, I'm a little slow, you guys. don't I get this? Sorry, I really am slow. I think I'm correct. But differentiate the right-hand side, I think you got a 1 plus 2x plus 3x squared plus 4x cubed, et cetera, et cetera, et cetera. Oh shoot, that's not what I wanted, is it? I lost the x to the fifth. So what am I doing?
Multiply.
Multiply both sides by it. And I think x to the fifth over 1 minus x quantity squared can be interpreted as x to the fifth plus 2x to the 6 plus 3x 7 plus 4x 8. I don't like this. Can you guys fix it? I asked. Can you guys fix it? Please? I know you can. So x to fifth times. Oh, you want an n out front? Well, the 0th term will give you coefficient of 0. But shoot, that doesn't seem to be working. So what do you want to do with the n?
-1
And
plus 1.
plus 1 I think works just fine. Now you can test me to see if I'm wrong. Plugging 0 in for n, yeah, the first term is x to the fifth. Plugging 1 in for n, yeah, the next term really is 2 times x to the 6. Or maybe you don't like the way I'm writing this. I'm just writing down what Sean told me. Maybe you would rewrite this, I don't know, it doesn't matter. This one means same thing. Doesn't matter which way you write it. I got a power series representation of one. Are you there? Okay.
So how do you get the 2, 3, and 4 in the top line?
2, 3, 4. Oh, you know what I did? I came in with my blue pen in my head. I differentiated with respect to x both sides. Only because I recognize this as being the derivative of what I had over there already with the geometric series, where a was equal to 1 and r is equal to x.
Aren't you using a factor of -1?
Say it again, I'm sorry, I didn't catch that.
Missing a factor of -1.
You're right, but I'm missing 2 of them. I'm missing 1 by saying, this is 1 minus x to the -1 power. I bring the -1 down, it becomes negative, but then the chain rule gives me another factor of -1. So you are right, I just have 2 of them, they input each other. That's why I don't know if you noticed, when I wrote, I stalled for a minute because I had to take care of the negatives in my head. Anybody want to shake me up? All right, if not. Have we had enough practice generating power series? The last few I cheated. I exploited what I know about a geometric series, particularly this one, which I rewrote this way. And I was able to generate power series for natural logs, inverse tangents, but I have to confess before the break, I did something very different. I was just simply suggesting that if this is a power series representation for a function centered about x equals a, then it's necessarily the case that CNs, the coefficients, are nothing more than these pieces right here. So I don't know if you noticed this, before and after the break, I used completely different approaches in generating power series representations for functions. I did. And if you're okay with that, let me talk about determining. Radii and intervals of convergence. Now, an interval of convergence is merely a collection of values of x for which I do have convergence for a power series representation by function. For example, let my function f have an output that's this. Suppose my function is expressed as this power series. Oops, did I miss an n, everybody? Look, watch. I meant to have n right there. Otherwise, it's not a power series. So I want to find all values of x for which I do indeed have convergence. Because I've got a factorial in here, how do you think I'm going to determine convergence? Because I have a factorial here, how do you
Ratio
think I'm gonna-
test.
Yeah, ratio test. And so with the ratio test, I'll come in, and I'll take the limit, as n plays this game, of the absolute value ratio of this. But I think that merely gives me the limit of the ratio of, is that an n plus 1 factorial? Over an n to plus 1 to the n plus 1. Divided by my a sub n, but I just simply multiply by its reciprocal. That gives me an n to the nth over n factorial. Sir?
So why are you leaving the x to the n out?
Oh, I'm not, I just haven't gotten there yet. But I did leave the negative 1 to the nth out because I'm taking a look at the absolute value of the ratio.
Like on the quiz, I included the negative 1 in the end because they cancel out. So,
I know, but they can't stop and give you a negative 1.
Right.
And you want the absolute value of the ratio, so it's got to be positive.
But the absolute value makes it positive.
Okay, that's fine. You just put in more steps then. You put in like 3 extra steps. I can live with that. By the way, I forgot the x's. So I think I'm left with the absolute value of x. And I'm taking the limit. I forgot to put it in as a thing. I don't know, you guys. You got a handle on what this thing right here guides to. I said, I don't know, you guys. You think I got a handle on what this thing guides to?
Almost.
1 over.
1 over n.
Yeah, you gotta pull out an n factorial from the top.
Is that a
And then
guess?
you can cross that out with the other one, so it's,
All right, I'll just do it. Limit as n plays this game. Do you guys agree n plus 1 factorial can be represented this way?
yes.
I won't touch the n to the n. Do you guys agree this first factor downstairs can be represented as n plus 1 times n plus 1 to the n?
Yes.
Oh, I lost my lingering n factorial downstairs. It's just that I get a heck of a lot of cancellation. And I think that leaves you with a natural log. Excuse me, I misspoke, sorry. Leaves you with a limit of something raised to the n, which is this. I think that leaves you with this. You guys, am I algebra okay? Am I skipping too much? By definition of E, yes, I agree that I think you can rewrite this as being equal to nothing more than 1 over E times the absolute value of x. Do you guys agree? Oh, wait a minute. I thought I was using the ratio test. The ratio test says I only have convergence if my ratio is less than 1. I'll set it less than 1 to determine the values of x for which I have convergence. But that necessarily implies the absolute value of x is less than E, which means we converge over one of the following intervals. From negative E to E, open, or from negative E to E, closed, or from negative E to E, one open, the other closed, or vice versa. And either way, I might say in English, my radius of convergence is just E. I just don't know if I converge at the endpoints. To determine if I converge at the endpoints, I gotta check what happens at the endpoints. I think there's a bit of work here. So if I ask you to determine intervals of convergence, typically you're gonna have to go ahead and see what happens in general, and then check each of those endpoints. I've got some more work to do. So allow me to come over to the left-hand board, where I do have more work. And it's checking endpoints. At x equals positive E, I think what I have is a corresponding specific series where x is being replaced with something everybody is no longer power series. This is a chapter 8 test of convergence. If I got the right chapter. And so plugging in for x, I think I'm simply left with this. And that's something I can check. I think add x equals negative e. I think I get this series. Excuse me. Do you guys agree? Do you agree?
Yeah.
Just one person? No tricks, by the way. Now, don't take this the wrong way. I'm not saying it's necessarily easy to actually guide these particular individual limits at the endpoint, but once you establish whether you got convergence here and here, you can make a decision on which one of these four corresponding intervals really is your interval of convergence.
That's a lot of work.
What's that?
That's a lot of work.
Yeah, I know it is. It is a lot. But I'm up against the clock.
I'm confused about what the interval of convergence means.
I think whatever the interval of convergence is, one of those four, is simply the collection of values of x for which my power series represents my function,
Okay.
and nothing more. It's sort of like with a hyperbola. You notice how when I got to x equals 1, I don't care how many terms I use, that power series isn't going to represent my function at x equals 1. And so there's a perfect example visually where you can see power series isn't going to have some kind of radius of convergence as infinity necessarily. It could. It sometimes does, but not always.
Which ones do? Off the top of your head.
If one of you value this limit, which you'll see in my next examples, if this thing of values to 0, you got an infinite radius of convergence. If this values to infinity, you get 0 as your radius. Now, I don't care what your power series looks like. Oh, shoot, there isn't one. Here's my general power series. I guarantee you, no matter what your function is, if this is a power series, it at minimum, is going to converge at x equals a. Because at x equals a, I just get 0 here. So for free, that'll happen. Let's see if I got some decent examples. I'm sorry, you guys, I have to do this. Here it might be too much work for me just to make up examples out of complete thin air. So if you guys can excuse me, I did make up some examples. How about this one? By the way, you guys, is it okay that n starts at 0? Because 0 factorial is
1.
positive 1. I know it sounds odd, but 0 factorial is positive 1.
Can you explain that? Why 0 factorial is positive 1?
I'd be happy to.
Alright.
So, I just pulled Randall, Brad, and David to the side. I put 3 chairs out in the hallway. I labeled one president, vice president, and treasurer. And I only want to concentrate on these 3 gentlemen. How many ways can I just close my eyes and grab one of these gentlemen, put him in the very first chair that's labeled president?
9. 3.
3 ways. I've only got 3 of you to choose from to put in the first chair. So I think the number of ways on the first subtask of choosing who's going to be president is 3. I got to multiply that by how many ways I can come back in this room, grab however many I could to put in the second chair for vice president. How many are left to choose from?
2.
And I'm going to multiply it by how many ways I can choose a remaining person for treasurer.
1.
And I think that's just simply 3 factorial. There's 6 different ways I can rank these 3 individuals. How about generalizing it? I think there's 6 different ways to rank any 3 items from a collection of 3 items. Is multiplication okay? This morning when I got up, I opened up one of my drawers. I had 3 shirts to choose from. I opened up another drawer when I got up this morning, and I only saw 2 ties. So would you guys agree there's 5 different outfits I could have chosen?